we will do is we will extend that addition, that nucleophilic addition, and we'll try to understand that equilibrium and reversibility in a reaction. But this equilibrium we studied, but today's class is a very important class where we will learn that how this concept of means physical concept like equilibrium that can be utilized for to make molecules, that is in organic chemistry, how we will use it. So very important class, today's class, I will say. So what we have done is, we have seen this is our carbonyl compound. When we put an alcohol R1OH, this is having a non-bonding lone pair, so it attacks to the pi star, this we all know. And what it will form? It will form this O minus ORH plus and then minus H plus and plus H plus. So two different steps, what you will get? You will get this OH and OR. So this is called hemiacetal. This is called hemiacetal. So look at the reaction. See this here, what we wrote is, this is in equilibrium. So that means this is in equilibrium. So what does it mean? It means that if you have an hemiacetal, that hemiacetal also can be cleaved to get what? Suppose I have hemiacetal. If it is decomposing, so what should I get? Can you please write? So hemiacetal, if it is decomposing, so what are the molecules we should get? So no answer. So what we should get? We should get, yes, carbonyl and alcohol. So these are the molecules we should get. So that's what we started our topic, that when people have dissolved the formaldehyde in water, they have found that the carbonyl peak is missing. There is no carbonyl peak. And similarly, when you dissolve an aldehyde in an alcohol, then this double bond won't be there. It will exist as a hemiacetal. But at the same time, you can get reactions with this, some other reaction, because they will be in equilibrium. This one and this one will be in equilibrium. So both are present. Last class we have shown it is 1:1 for some compound. In fact, this is not even 1. This is probably more or less, maybe 0.1 or even less. So that means most of the equilibrium will be in this side, not at the product side. And we have also studied, we have also learned, not studied, we have also predicted that suppose in this hemiacetal formation, if I use a catalytic H plus, okay, so will it be advantage for us or disadvantage? Advantage, yes, because we, in presence of that acid, what I should get is this OH plus. So this is some oxonium ion, so which is more electrophilic character is there. Since its pi star is energy is down, so this is more electrophilic. More electrophilic. It acts as a good electrophile. Electrophilic. So that we have seen. So that means what we learned is that hemiacetal to aldehyde and alcohol is easy. Very easy. You can get it. And also what we learned that this process can be expedited by the addition of acid. So that means this hemiacetal formation, this reaction we can term as acid catalyzed. We have seen this, acid catalyzed. So if it is acid catalyzed, then mechanism will be slightly different. It will be plus. So again, one more means, so this step is not required. So catalytic acid will convert that, acid catalyzed. So hemiacetal formation also can be base catalyzed. Also can be base catalyzed. So what is the mechanism? Base catalyzed. So that means in presence of base also it is possible. So what is the mechanism? Mechanism is this. So suppose if you have R1OH in presence of OH minus, what you will get? You will get R1O minus. So R1O minus is a better nucleophile. It is a better nucleophile as compared to this ROH. As compared to this ROH, it is a better nucleophile. So its homo energy is higher. So this is more reactive. So this can react directly to this. And obviously it will be in equilibrium. So then protonation will happen and you will get the hemiacetal. So here you will get OH minus, and this, what will be the fate of this OH minus? This will be act as an water. You will get water. Then this water will be protonated. From this water it can take a proton. So what you will get? You will get OH OR plus OH minus. See, again you are generating. So this is the beauty. Why it is called catalyzed, base catalyzed or acid catalyzed? Because you are generating again this OH minus. So you start it, you again got that, so you can do the next molecule. You do not need an equivalent amount. Same logic for H plus, because here also one H plus you will get. So that means what we learned is this acetal formation, hemiacetal actually, can be expedited in presence of acid. The mechanism is slightly different. In presence of acid, you are making your aldehyde better. In presence of base, you are making your alcohol better. As a, means you are converting your alcohol as a good nucleophile. Okay? So that is the strategy we are doing. Okay, so we can keep it. So now this hemiacetal, what it can do is, hemiacetal in presence of acid H plus, it can protonate further. So suppose it will be protonated here. This one there is a protonation. So what I should get is this OH2 plus OR. So then what is happening is, after the protonation, after this protonation, this is becoming a good living group. This is becoming this one OH2 plus. This becomes a good living group. Good living group. So good living group means it can be removed very easily. So this bond become weak actually. So you can very easily cleave this bond. So that is so this bond will be easy to cleave. So obviously, so then what can happen? This one can attack and this will go. So what I should get? I should get this double bond OR plus R1 should be mine. R1, R1, R1. So that is the electrophile. See, here it was OH plus. Now we are generating one more electrophile. So oxonium ion. Oxonium ion. So can you tell me what is the property of this oxonium ion? Whether it will react faster with a nucleophile as compared to your ketone? What do you think?
Yes, sir.
Yes, same logic. It will be same logic because this is becoming more. So electrophilic character. And why electrophilic character? Logic is same. Its pi star energy is going down. This becomes now a good electrophile. Good electrophile. So then you have suppose excess alcohol. So in this condition, what I am doing? I am taking excess alcohol. So that means not 1:1, slightly means more than 2 equivalent. So one more is there. So alcohol is present, more alcohol. So this alcohol can act as a nucleophile. So you will get this. So you will get OR1 and then OR1H plus. And subsequently this one, this minus H plus will be there. And if it is minus H plus, then what I should get? This is minus H plus. This one, this H plus will be removed. So water can abstract actually. Water will abstract and you know the mechanism. So what I should get is this type of molecule. OR1, OR1. So this is called acetal. Acetal. So this is called acetal. So OR1. My 1 is not perfect, this one. And here, this is very important step. So you say one molecule of water is, we are losing. So one molecule water we are losing. So now, if I write the overall, means if I write the mechanism, now can you tell me that, so in base medium, suppose if I have a base, in the basic medium, can I get acetal? Means I have shown that up to hemiacetal I can get here. But can I get acetal in presence of base? Is it possible? From the mechanism. That is the reason why we are interested on mechanism. Always we prefer mechanism. Because from the mechanism we can predict whether this reaction we can perform this reaction in presence of acid or base. So is it possible that this reaction will go in basic medium? What do you think? What is your prediction?
It won't,
So why?
because the water won't be removed if
Yes. So water won't be removed because to make this acetal, we need an oxonium ion. We need an oxonium ion. That is possible by the removal of water. And this removal of water is possible only in presence of acid. Only in presence of acid. That's why acetal formation, we should not get acetal in presence of a base. But hemiacetal is okay. So acetal formation, what we need, so we can write it now because it is matching with our mechanism. So for acetal formation, see acid is must because to remove water. So this is the very important thing. So we need acid. If we just mix it without acid, reaction won't go. We need some acid. Okay. So now what I am doing is I am just removing the mechanism part and yeah, so this one. So now what is my mechanism? So my not mechanism, my overall reaction is this OR1 plus water. So catalytic H plus is required, that we already know. This is there in the mechanism. Okay. So now this reaction is in equilibrium. This is the important thing. This is in equilibrium. So that means this and this is in equilibrium. So to get acetal, what should be my strategy? If I want acetal, so what should be my strategy? These are in equilibrium. Suppose maybe equilibrium constant is good like 0.1. So 1 means also, if it is 1, that means also at equilibrium, this is 50%, this is 50%. So your yield is theoretically maximum 50%. So that is not good for an industry and not great for a methodology. So then what should I do to make this conversion in a facile manner? So what strategy I should use? So this is in equilibrium.
replace the CH3s with hydrogens.
Sorry?
Replace the CH3s with hydrogens. Only hydrogen.
But then also reaction will be okay, but it is not a great. So you are actually, what you are doing, you are increasing the reactivity of the carbonyl, right? You are increasing the reactivity of the carbonyl because in the acid means if you have a ketone, it is more sterically congested. That 107-degree attack is not that facile. That is the reason we have learned that why ketones are less reactive as compared to aldehyde. So that is one, okay, that is probably one reason. So what I can do is this, that I can use excess R1OH. So this is one my strategy. I have to use this in excess so that it will drive the reaction. Next strategy should be, if I remove water from the reaction mixture, remove water from reaction mixture, will it be helpful? If I remove water from the reaction mixture, means whatever water is forming, I am just removing that from the reaction mixture. Will it be helpful then?
Yes, sir.
Yes. So according to La Chatelier principle, my reaction, that equilibrium now will be forwarded to this forward direction if I remove the water. So that is my another strategy. So how to do that? So to do that, what I have to do is, I have to reflux. I have to use a solvent called benzene, or you can also use toluene, which will form some azeotropic mixture with water. Then under reflux condition, and you need an apparatus called Dean-Stark apparatus. Dean-Stark apparatus. So using this apparatus, you will be able to remove water. So what is the use of this? This is useful to remove water. Remove water. So another thing is, whatever acid you are taking, you don't take any aqueous acid. So that means aqueous HCl you don't take. Don't take aqueous HCl, because aqueous HCl means you already have some water in the mixture. So I should take some anhydrous acid. So third is, you can take some anhydrous acid. So I should not use any concentrated HCl, because concentrated HCl also means that it is only probably, I have to check, maybe either 35% or maybe 65%. So whatever it is, it contains lot of water, even it is concentrated HCl. Anhydrous acid. So for example, what are the example? You can use para-toluene sulfonic acid. Para-toluene sulfonic acid. Sulfonic acid. It is as good as sulfuric acid, but it is also soluble in benzene and toluene. That also you need, because all your reactants should be miscible. Otherwise, they cannot perform the reaction. Also, you can also use dry HCl. Dry HCl also you can probably use. So dry is okay. Dry HCl means HCl gas. You can use HCl gas. Okay. So these are the strategy we should use to get an acetal. But now you tell me whether what should be the stability of acetal. Stability of acetal. So whether they will be stable in HCl means acid, stability of acetal. What do you think? Stability of acetal. So this is the topic. So whether they will be stable in acid or base. So that is the question. So that is the beauty of equilibrium. Why I told that today's class is very important class. See, this is in equilibrium, right? Every step is in equilibrium. In presence of acid also, right? In presence of acid. And this is para-toluene sulfonic acid or TSOH we can write. So this is the condition. So we have alcohol, we have benzene, toluene, Dinstark apparatus to remove water, and we also need some acid. So paratoluene sulfonic acid. So the why equilibrium is the beauty is, so every step is in equilibrium. Now you suppose if you have acetal and you have aqueous HCl, means aqueous acid, what will happen? They will now go to backward direction. They will go to backward direction because your forward step is irreversible. That means your back means you should also get backward. Means suppose if I know how to walk this, so then I can also know that how to walk back. So that is the beauty of this reversible reaction. Since it is a reversible reaction, what is possible that if you take an acetal in presence of water, means aqueous HCl, what will happen? They will just go to this state, ketone and alcohol. Is it clear or not? Why I need water? Because at some point, if you look at your notebook, here I have shown, so in the equilibrium when water is removing, at some point here for this step, for example, what is required? This water should act as a nucleophile and you should get that intermediate. So water is required. Is it clear or not? This is principles of microscopic reversibility.
Sir, I have a doubt.
Yes. You have a doubt?
I have a doubt.
Yes.
If acid is the one which is required for removing water so that the reaction proceeds in the forward direction, and acid is the reason where we can produce H2O and then remove it, then how does acid make it go backward? Like aqueous acid make it go backward?
Yes. So see here how I go back now. How I go back? See, from here to here, this step, suppose what is the mechanism of decomposition of this acetal? This is the same mechanism, that instead of minus H plus, if I go this direction, I have to have a plus H plus. So that plus H plus will join here, then this will attack, this will go. So forward direction I have done an addition. So reverse reaction, this will be a removal because this is also a good leaving group. Then I will get this. If I have water, then this water will attack, I will get this, and then I should get the back. So that's why this protonation step is to destabilize this acetal. I need this protonation. I now need this protonation. Now let us write this positive. I need this protonation. Is it okay?
So only the acetal should be kept in basic conditions so that no protonation occurs on the acetal, but the rest of the reaction has to happen in an acidic condition to form the acetal in the first place.
But you need what? You need water as well. You need not only acid, you need also water. Is it clear? Because if it is the backward reaction, you need water also, because this is the step. Water, see, forward reaction there was minus water. So backward reaction, that means this is a good electrophile. So water is a good nucleophile. So water will attack. So what I should get? I should get this OR1 and OH2 plus. So same step. This is principle of microscopic reversibility. So the forward reaction, if it is reversible, the backward reaction also follows same mechanism. If forward reaction, same mechanism to product, then product to starting material also, it will follow the same mechanism. This is the principle of microscopic reversibility. Very important concept. That's why we wrote reversibility. Now can I predict it, this one? So like that, now it can go again back reaction. If I write that now again this will be minus H plus H plus, so that now this will be removed, this will be plus. So OR1 plus OH. So next this OH will come, this will be removed, and subsequently you should get your ketone. So same mechanism. Forward reaction also mechanism, same mechanism. Backward reaction also same mechanism. Principle of microscopic reversibility. Very important concept. So now can I predict that acetal, if I keep my acetal in aqueous acid, whether they will be stable or they will decompose? What should be my prediction? Yes. And what product I should get?
Back to the ketone and the
Alcohol. Okay, good. So we should practice little bit. So this is very important concept. Conceptually very important. So what we learned today, how to drive equilibrium. Means suppose a equilibrium is in this side, how to drive it. So you remove that. We also learned that if you have this, how to destroy that. You add water and acid, you can come back to previous one. So acetals, whether they will be stable in basic medium. In the basic medium, what about their stability? What is your prediction? Acetal. Acetal means this one, not heavy acetal. In the basic medium. Whether it will be stable or unstable. So, can you synthesize acetal in presence of base? First question.
No, sir.
No.
Absolutely, may not be formed.
So that means acetal means I should not use, acid must. No, base cannot do that. Base can do up to hemiacetal. So that means there is no role of the base. So you cannot change the equilibrium. So acetals are stable in basic medium. And also if you look at the structure, base means what? Base means a good nucleophile. So here, where is the good electrophilic center? There is not very good electrophilic center. Only these are sigma star orbital. See, what are those? These are all sigma star orbital where you have to donate. So that is definitely not easy. So our concept is working. So acetals, stability of the acetal. So acetal is unstable in acid, but which acid? Aqueous acid. This is very important. Aqueous acid means you need some water. Otherwise, because this water is required for that backward step. So aqueous acid is required and stable in alkali. They are stable in alkaline solution. And I hope now we will not memorize. We can also understand from the mechanism. So that's why the course reaction mechanisms in organic chemistry. Okay. So what is the advantage? Okay, so this is one thing. Another thing is how to drag the equilibrium. There is one more step which I did not write. So how can I make it forward equilibrium? So one is I wrote that to remove water, then with the Dean Stark apparatus and benzene and toluene, use some also acid and another, and also excess alcohol you use. So what you can do is also this, we can write maybe third probably point. What you can do is you can use a diol instead of an alcohol. You can use a diol. Diol means what? You have two alcohol. Two alcohol. So the advantage will be this. Suppose if I now give a proper example, catalytic PSOH, paratoluene sulfonic acid. This is an acid catalyst. Benzene reflask in Dean Stark apparatus to remove water. So what I should get is now, and also this is my now alcohol. CH2, CH2, OH, and this is OH. So what I should get? So this alcohol will attack, or everything will happen. Second alcohol also will come from the same molecule. And last class we have already discussed that intramolecular reaction is kinetically and thermodynamically more favorable as compared to intermolecular reaction. So this is one more strategy. You can use a diol to get an acetal. So you can drag the equilibrium. The concept is here. Suppose to make an acetal, what you need? You need two molecule of this. So three molecule, you are getting two molecule. So entropically, this is not favorable. So if you use a diol, what is happening? From two molecule, you will get two molecule because the other molecule is, we are not writing, but we have to remember that is other molecule is water. So this is one more strategy, that how can I play with the entropy factor and I should get my acetal formation. So now the question is, why these are important? Why these are important? Why we are studying this? So I will give an example that why this acetal formation is useful in organic synthesis. See, organic means our ultimate aim is to synthesize molecule, because we need a variety of molecules for our daily purpose. Okay, for our daily purpose. See, we are taking medicine, those are also organic molecule. We have to synthesize. So this chart also, some polymeric component is there. The monomer of that polymer is also we have to synthesize. So we are heavily dependent on organic synthesis. So our ultimate goal is in the synthesis. Okay, so one example I will show, that suppose I have this molecule bromo CH2 CH2 C double bond OH. So this is my molecule, from where this is my molecule I have. I want to make this, that CH3 CH2 C triple bond C CH2 CH2 C double bond OH. So that means what? That means, see, this part is there, 1, 2, 3, 1, 2, 3. So this is there in my starting material. What I have to do is I have to only join this part. I have to only join. This is the part I have to join. So how I can join is very easy, because I can do a substitution reaction. If I have, I know this is Rx, this is Rx. If I give a nucleophile, then I will get RNU. And if my nucleophile is this, then I should get this. So that is the strategy. So if I use this CH3, CH2, C triple bond C minus Li plus. So suppose this is my nucleophile. Okay, how I should get? I should get from this CH. So this I know that this HOMO can act as a good nucleophile. So this is a good nucleophile. Good nucleophile. So this nucleophile can attack this is a nucleophile. So this can attack CBr sigma star orbital. CBr sigma star orbital. Then I should get my desired product. The question is, this is the only product or not?
So it could
It can
also
also
attack
attack
the
to
carbon.
carbonyl carbon.
Yes, because it has one more pi star. It has a pi star also. Here also this can be donated. So if this is attacking, if this is the pathway, then I should get this is the molecule. So that means my strategy is not a great strategy. See, after protonation, I will get OH, then CH, and I should get C triple bond C, CH2, CH3. So how to overcome that? How we should not do that means I need to make this molecule. See, now this is my target. Suppose the company give me this target that you have to make this, or your supervisor may told that you have to make this molecule for your PhD thesis or master's thesis. So what we can do is, so I'll come back to that point. What we can do, we can use this acetal chemistry. This acetal chemistry is that's so important. Acetal chemistry we can use it. So how to use the acetal chemistry is this. So whatever we learned, we will apply now. So this acetal chemistry we will apply. So now let us apply. So what I have to do is the more reactive one. So this is more reactive because this is pi star, energy down little as compared to that. So this is more reactive center. Even more product I should get this. So the more reactive one I don't want now. So I will use acetal chemistry. What is the chemistry? Very simple. So what I will do is that I will use this diol CH2, CH2, OH, OH. I will use paratoluene sulfonic acid, obviously catalytic, and you can use benzene as a benzene and reflask. Reflask in Dinstark apparatus to remove water. What you will get? You will get this. Because this aldehyde will form an acetal. What I will get? I will get formation of acetal. So this is the step. What is the step? Formation of acetal. So what I should get? Br, CH2, CH2, C, this is my H, this is oxygen, this is oxygen, this. So this CH2, CH2 comes from here and here. Okay. So now you have, now here you do not have any pi star. Now if you have a nucleophile, the same nucleophile if you add, now second step after formation of this acetal, now if you put this nucleophile, then this nucleophile will only attack CBr sigma star because there is no center here. So it will attack. So what you should get is this CH3, CH2, C triple bond C, then CH2, then CH2, then C is oxygen, a 5-membered ring. This is my hydrogen. So this I should get. And now what I will do, that same acetal chemistry concept I will use because I know I can form acetal. After formation of acetal, I have performed my reaction. Now I can also decompose my acetal in presence of aqueous HCl. So this is the beauty. So what I should get, that now what I can do, I can decompose because I know that acetals are not stable in aqueous acid. So what I can do is I can use aqueous acid. So aqueous acid, what will happen? This acetal decomposition. So when it is decomposing, I know acetal decomposition, I should get the alcohol and the aldehyde. So I should get this alcohol and I should get this aldehyde. So this is my strategy. So this is the beauty of acetal chemistry. So acetals, so this is the molecules you are getting. So is it fully understandable, the acetal chemistry? So this strategy we call this in organic synthesis protection and deprotection. Protection and deprotection. So this is the topic. You can just turn this. So what I am doing, I am protecting first step, formation of acetal. So this means I am protecting the aldehyde, protecting my aldehyde. So this is the step, first step. So then you perform your reaction, and third step is deep protection. So whatever alcohol, aldehyde you have protected, now you deep protect. So deep protection, protection and deep protection to get to a more reactive substrate, you can bypass actually. This is the strategy. Okay, so acetals are very beautiful. It is performing, and then also it is helping you, and then also it is not asking anything, any help also. So good character, acetal. Okay, so now we have completed the alcohol addition to the aldehyde. So similarly, what is possible that if you use other nucleophile, so we have also seen that if you have cyanide, that Cn minus can attack. If you use amine also, definitely amines will attack.